Okay, let's start. Good morning. So we have a couple more items to discuss about continuity metric spaces before we can switch over to differentiability, differential calculus, or calculus proper. And I wanted to remind you of the basic statements about continuous functions that you learned from 3210. So before I start, maybe I should ask, are there any questions about anything? I started grading the midterm. So far it seems good. Yeah, and because of the events last week, I'm not going to be taking attendance this week. So if you feel like you're not in the mood, whatever, you're not going to be punished for not attending the class. But of course, in general, you are supposed to come to class. OK, it's part of the experience. Part of learning math is somehow getting exposed to these complicated ideas. And then after a couple times, you think about it, you read about it, and so on. And then eventually it starts sinking in, a lot of these things. OK, so let's go over all of these things. So continuity and continuous functions. Yeah, there's actually one more thing that I might want to add, but let's go over these. Monotone convergence theorem. OK, if you have a sequence of real numbers that is bounded and monotone, so non-increasing or non-decreasing, so you don't go sort of up and down. It's either always going up or staying constant, or it's going down or staying constant. Then the limit exists as a number. That was the monotone convergence theorem. Now, I had told you that it's a good exercise to go back to your 3210 notes and have a look at whether or not any given statement can be generalized. And note that this, because of this monotonicity, increasing or decreasing, really requires a one-dimensional situation, right? So if your signal is going up or down, then you can talk about increasing this or decreasing this. But in a general metric space, or in a general norm space, R2 for instance, this doesn't quite make much sense. So we're not really going to have something like this. So that's a problem. This is something that we're not going to be able to generalize to higher dimensions, at least to the extent that we're going to discuss it. But in a sense, we have this thing, nested interval property, which says that if you have a decreasing sequence of closed and bounded intervals, so I have closed and bounded intervals, and then so for instance, I1 is a closed and bounded interval like this. And what does it mean for a sequence of intervals to be decreasing? I want I2 to be yet another closed and bounded interval, and I want it to be a subset, possibly equal subset to I1. Okay, so if this were I1, maybe I2 is something like this. And then I want to keep going like so. Okay. So this would be a decreasing sequence of intervals, or in general, decreasing sequence of subsets. And it says, nested interval property says that if you were to take the intersection of all of these, there's at least one point in that intersection, right? And it turns out that even though, in general, we can't quite talk about intervals, we're going to see today, we can talk about closed and bounded, but really, we're going to talk about what is called compactness. That's the proper way to generalize it. And basically, the same statement holds in arbitrary metric spaces. And this, we're going to call the Cantor intersection property, or theorem. So this we're going to be able to generalize to arbitrary metric spaces. And it turns out that within the theory of metric spaces, you can really make sense of what it means for two subsets to be L distance from each other. So really, you can talk about the collection of subsets itself as a metric space. And so people who are interested in things like computer vision is interested in ideas like this, but we're not going to push it that far. Because somehow we're not going to sort of develop metric spaces by themselves. We're really sort of doing just enough so that we can switch over to differential calculus. Bolzano-Weierstrass says if you have a bounded sequence, then there is a subsequence, right? So this is like a strictly increasing function in your time variable, such that when you take the subsequence, x bullet, composed with j, it has a limit. Any sequence, any bounded sequence has a convergent subsequence. It turns out that this has generalizations, but it's going to be somewhat tricky. Certainly, it's going to have a generalization to Rd or any finite dimensional normed vector space. But more generally, it turns out that in arbitrary metric spaces, this can fail. And I'm going to give you examples, at least for Rd or finite dimensional norm spaces in general. Okay. Next up is the maximum principle, or extreme value theorem, which says that if you have a closed and bounded interval I and a continuous function on it, taking real values, then indeed this function attains its max and min. Yes? Turns out this generalizes to arbitrary metric spaces. Again, maximum principle instead of having a closed and bounded interval. And really, when you think about the proof, whatever proof you have, you're actually not using the fact that this is an interval. In fact, you can take any subset of R that is closed and bounded. Of course, we don't know what it means for a subset to be closed within the context of 30 to 10, which we're going to have to discuss. So we're going to have to define what it means for a subset to be closed in such a way that closed intervals are closed. Okay? And likewise, we're going to define something called open subset in such a way that open intervals are going to be open. Okay, so this really is something that we're going to get rid of, and it still applies. IVT, intermediate value theorem, it says that if you have a continuous function defined on a closed and bounded interval, then, if you have a continuous function defined on a closed and bounded interval, then within any two outputs, if you take some other height, that too is attained by f. So the point is, if this is my I, and f is some function, and if these are two heights, such that I know that f attains y1 and y2 here, in fact, f attains any height in between. In other words, the graph of a function that is continuous cannot be, so there could be no teleports, basically. And again, when you think about this, the proof of it, this, on the other hand, doesn't use the fact that this set is closed and bounded. It uses the fact that it's an interval somehow. So in a sense, this notion of an interval in higher dimensions, or more abstractly, is going to generalize to either the notion of a path-connected subset or a connected subset. Okay. So that closed and boundedness we're going to get rid of. Next up is sort of like a joining of all of these ideas. It says that if you have a closed and bounded interval and a function, arbitrary function defined on it, taking real values, then you have a bunch of relationships, bunch of ideas. One of them is continuity, the other one is monotonicity, the other one is the image being an interval itself. So first part says, if you have a continuous function, then its image itself is an interval. So continuous functions takes intervals to intervals. Second, it says if you have a strictly increasing or strictly decreasing function whose image is an interval, in fact, that function is continuous. And third, if you have a continuous function that is strictly or increasing or decreasing, then in fact, it has an inverse, and its inverse too is continuous. In other words, this function that you started with is a homeomorphism between the domain interval or input interval and the output interval. Somehow, versions of this still apply in higher dimensions. So for instance, this we're going to interpret as, oh, the image of a connected set under a continuous function is continuous. Or you could also interpret it as saying the image of a compact set under a continuous function is compact. So there's multiple ways to interpret this. But again, like I said before, the strict increasing or decreasing is going to be a problem. In higher dimensions, you really cannot really make sense of this, and here too. And this is really the starting point of what is called the curse of dimensionality. Right? So if you have a function that takes so a scalar as an input and a scalar and gives back a scalar as an output, then you can only do so much. In higher dimensions, imagine a function that goes from 2-dimensional space to 5-dimensional space. Well, how are you going to sort of like handle this? How do you even make sense of increasing this or decreasing this? There's no, in a 2-dimensional space, there's no left and right really. There's something called an orientation that we might look into later, but this is what we have so far. Any questions about any of this? You should have encountered these theorems in 3210. I just wrapped everything up, and it's like a summary. And I hope this also justifies why I'm using this mesh notation. You see, so I can compress a lot of information. OK. So now I'm going to introduce some terminology so that we can make sense of phrases like closed, bounded. Oh, we can make sense of bounded, but I would like to make sense of closed. I would like to make sense of an interval in abstract. We know what it means for a function to be a homeomorphism, what it means to be continuous, and so on. So we have a couple of things to define. So let me say topological terminology. So this is definition. Topology jargon, let's say. Some of you are going to be taking the topology class after this. And in that class, you really sort of focus on all of these notions. I'm just going to stick to very basics. And there's two ways, ultimately, to define everything I'm going to define here. One of them is it uses sort of like this more general understanding of topology. But I really want to define openness, closeness, compactness, and so on in the context of metric spaces. And so because of that, I'm going to define pretty much all of these notions using sequences. At least for analysis, it is very convenient, I think. And it's going to cut down on the terminology that you're going to have to learn. OK? So let's X be a metric space, and A be a subset. OK, let's start with closed. I'm going to call A closed if any sequence in it that converges to some point in X in the larger space, in fact, that limit has to be in A. If for any A bullet sequence in A, and for any X infinity in X, if A bullet converges to X infinity, in fact, X infinity has to be in A. Limits of convergent sequences have to be within the set. So closed means closed under limits. OK? And of course, closed intervals are closed in this sense. If you were to take a sequence in an interval that is closed, if it converges, that limit has to be inside that closed interval. OK? I'm going to call A open. Somehow, openness is the dual notion. if, well, perhaps the best way to define it in this context is to say that given any point in A, there is some radius r such that the open ball centered that point that you chose with that radius you find is completely inside A. For any A0, there's a radius such that the complete ball, open ball, centered at A0 of radius r is a subset of A. So these open balls, I told you, you should think of as sort of like a cloud, which means that this openness is really about being closed under perturbation. So you have one point and you sort of, push it around just a little bit, and if you're careful enough, you're not going to be able to escape A. So openness is closed under perturbation. I'm going to call A compact if essentially the conclusion of Bolzano-Weierstrass holds. That is to say, if any sequence in A has a subsequence that converges to some point in A. Let me just write it like this. This is my abbreviation for saying that A bar bullet is a subsequence. A bar bullet converges to A bar infinity. Okay. Okay. What is next? Let's define disconnectedness and connectedness. I'm going to say A is, let's start with path connectedness. It's easier. Path connected if given any 2 points in A, there is a continuous function from some interval into A that connects the two. If for any, let's say, A1, A2 in A, there is a gamma, let's write it like this. There's a continuous function from 0, 1 closed to A, such that gamma of 0 is A1, gamma of 1 is A2. So you get to sort of interpolate. And then finally, A is connected if you can't basically separate it. So it's better, perhaps easier to define what it means for a subset to be disconnected. Disconnected if there are two open subsets in A. There is U1, U2. You can take it in X if you want. Open, non-empty. Such that they don't intersect, and their union covers A. And of course, I'm going to call A connected if it's not disconnected. So this is a complicated state of affairs. It's a bunch of definitions, and it takes a while to get accustomed to all of these definitions. You're going to have to keep going back, reading the definition over and over again. And somehow all of these definitions are related to each other. And in a sense, this is sort of the starting point, in a sense, of topology. Really, in topology, what you do is you take a set and you define what is called a topology on it by declaring which subsets are open. And then that turns out to be just sufficient, just enough to talk about continuity, homeomorphisms, and stuff like that. I'm not going to go that far because I don't think it's going to be useful in our class. And if ultimately, if you end up taking the more advanced class in topology, you're going to spend a lot of time on the interrelations between all of these ideas. Here are some very nice exercises, of course. First of all, a subset is open if and only if its complement is closed. Okay, that's a very nice exercise. Some exercises. So A closed if and only if A complement, which is X take away A, so the collection of all those points that are not in A is open. Compact implies closed, for instance. Path connected implies connected. So connected means not disconnected. What else? For sanity, let's think about subsets of the real line. Any closed interval is closed. So lambda rho is closed. Rays are closed. Oh, lambda to infinity. Minus infinity to rho. Open intervals are open. Open rays open. In fact, maybe I should update it like this. Any closed and bounded interval really is compact, but rays, even though they are closed, they are not compact. So maybe I should write it like that. So compact, hence closed. Rays, closed rays, not compact, but still closed. Okay, so these are different ideas. Okay. So the benefit of, instead of using closed and bounded intervals and stuff like that, is that if you were to take, for instance, in fact, an arbitrary number of possibly disjoint open intervals, take their union, that too turns out to be open. So somehow openness and closedness, even though they match with your understanding from intervals, they generalize to arbitrary sets. So maybe I should add it. Probably I should add it there, actually. But let's write it here. Arbitrary union of open sets is open. Finite intersection of opens is open also. Okay, there's a bunch of sort of statements like this that basically allow you to operate. I realize this is a lot. Don't worry too much. In time, you're going to get accustomed to these. And I'm going to keep reminding you the definitions. OK. Good.
Can I ask a question?
Yes.
So A is a metric space here?
A is a subset of X. So it has a, so the moment you take a subset of a metric space, we think of it as a metric space in and of itself by just restricting to metric. So this was a subspace metric. Yeah.
I'm confused on the analogy between that and the intervals from the previous definitions. Like how does just like the closeness of an interval relate to the closeness of this metric space A?
Right. Let's see. I'm going to have to delete some stuff. Let me just delete this part. So for instance, I guess I should first start with this. Are you happy with the statement that a closed ray is a closed subset? If I were to take a limit, if I were to take a sequence in 0 to infinity, if I were to take a sequence of non-negative numbers, okay, example. Can you tell me that it is convergent?
Yes.
No, because 1, 2, 3, 4, 5, 6, 7, 8, it doesn't converge.
Okay.
So if it doesn't converge, I cannot say anything. But if it does converge, that limit has to be a non-negative number. Mm-hmm. It cannot converge to -1, for instance. If exists. So this is how closeness work in the case of rays. But for instance, I can think of the following. Let's look at the plane. And let me let A to be the first quadrant. OK? What does this mean? It's a set of all those x and y's such that, let's say, x is bounded from below by 0, and so is y. Right? That's how I can define it. Let me just draw the picture as well. So I have the plane here. And I'm looking at, so this is my x with the standard metric, Euclidean metric, and I'm looking at this subset. This is a closed subset. I'm saying. Why is that? If I were to take a sequence in A, in the first quadrant, I don't know if it converges, because again, maybe I'm looking at n, right? 1, 1, 2, 2, 3, 3. Maybe it goes to infinity. But if it does converge, then in the limits, the x component has to be non-negative, y component has to be non-negative. Which means that by taking a convergent sequence, you're not going to be able to escape this A. There is no way that you can come up with a sequence in A that converges to -1, -1. Okay? You cannot be converging here. Does this kind of make sense? Okay. Now what I'm saying is that even if you didn't have access to this intuition, let's say that your X is a more complicated space, this still makes sense. Okay? So here's an example. We said that there was something called C0 norm on the space of, let's say, continuous functions. Example. Let me let x to be all functions defined on 0, 1, taking real values, bounded functions, with the metric, which is a C0 metric, sup of f of x minus g of x in absolute value, where x varies between 0 and 1. That's a norm, or that's a metric. And let me let A to be the space of continuous functions, continuous and bounded. Oh, I can just delete this. This is the space of all continuous functions. Maximum principle, or the extreme value theorem, says that any continuous function on a closed and bounded interval attains its max and min, which in particular means that A is a subset of X. So A is a metric subspace of X. But furthermore, if I were to take a limit here with this metric, that limit is going to be within A. So A is a closed subset. In 3210, what you said is that uniform limits of a sequence of continuous functions is continuous. Okay. Maximum principle implies that A is a subset of X if f bullet is a sequence of continuous functions that converges uniformly, right? Not necessarily pointwise. In the pointwise case, it doesn't work, but uniformly it works. Then, in fact, this limit has to be, again, continuous. Then, i.e., A in X is closed. It's a closed subset. I'm taking a limit in A that converges to something in X, but I did some epsilons and deltas, and I realized that limit has to be in A, in fact. Same thing with, for instance, B, Riemann integrable functions. If I were to take a uniform limit of Riemann integrable functions, the limit too is Riemann integrable. That's also something you learned. That's another example. So B, Riemann integrable functions also closed. Differentiable functions turns out to be not closed, for instance. you can approximate a non-differentiable function using differentiable functions. What's an example? Let's continue. Continued. C, let's say C1, once continuously differentiable. C1 functions here. Of course, once continuously differentiable functions themselves are continuous, which means that they are bounded. So this is a subset in X. This is not closed. So here's an example. Nope. Remember, I told you differentiability or continuous differentiability is something that is required. It's a property that has to hold everywhere. And so for a function to be not differentiable, all you need to do is to break differentiability at one point. So maybe let's look at sort of like a tent map, something like this. This is not differentiable. Can I approximate it in a uniform metric using differentiable functions? Well, you can smooth this corner out, right? So you can sort of start like this. This is F1, let's say, and sort of make it turn tighter and tighter and so on. So you start with a very round function and you slowly sort of shrink it to get the cornered function. So each of these, so this F1, F2, F3, these are points in this subset. F infinity, I'm going to leave it to you, that it's a uniform limit, in fact. But the limit is not differentiable. So this is not closed. Does this make sense? Okay. So in a sense, closeness and openness, these things are about approximations. You have a certain object and you're trying to approximate it, and you're asking, if I'm using objects of a certain type, objects that have a certain property, is it guaranteed that in the limit too, the same property holds? If yes, that's closed. If not, then that's not closed. Not closed doesn't mean open, by the way, okay? This is an important thing. This is math, of course. Okay, this is important. So there are subsets that are both, that are neither, or one or the other. Okay, so imagine, for instance, an interval that is closed on one side and open on the other side. Is neither closed nor open. If I were to look at, for instance, 1 minus 1 over n, that's a sequence in this set, converges to 1, the limit is not in there. It's not closed. Okay? All you need to break closeness is to come up with some sequence that converges. Okay? If you can come up with one sequence that converges to some point outside your set, that means that it is not closed. It's also not open, because remember, openness was about taking a point and moving it around just a little bit. But if I were to take 0, you don't get to say, I'm only moving right or left. You have to allow in every single direction the small sort of perturbation. So you perturb, you start with 0, You perturb it just a little bit, possibly you're leaving the set. So imagine this, right? So you're sort of doing some experiments on your computer, whatever, and you have some number that is very small. Maybe on the computer you see 0. That doesn't mean that it's 0, right? Maybe you're sort of leaking some information. So. Any other questions? It's a very good exercise to sort of look at, oh, here's a metric space, here's a subset, is it closed, open, whatever. Is it compact? These are very important ideas. Maybe we should also think about this. I gave you as an exercise that closed rays, while they're closed, they're not compact. Compact means conclusion of Bolzano-Weierstrass holds. That is to say, you get to take any sequence whatsoever, it is a convergent subsequence. So example, so 0 to infinity, not compact. Again, to break compactness, all I need to do is to come up with one sequence that I know for sure has no convergent subsequence. Convergent subsequences. What's a sequence here that has no convergent subsequences? Yeah, 1, 2, 3, 4, 5, 6. It doesn't matter how you're going to sort of sample out the subsequence. It's never going to converge. And in fact, here's a very nice exercise. This is a restatement of the Bolzano-Weierstrass, you know. It says that any closed and bounded subset of the reals is compact. Let me write it here. So let A be a subset in the reals. If A is both closed and bounded, then it is closed. It is compact. It is compact. And in fact, this is a phenomenon which you can show with what you know so far. So exercise. Then it is closed and bounded. Sorry. So in a sense, compactness is a notion that you can factorize into closed and bounded. Okay? Turns out that you cannot do this all the time. Oh, well, this way you can do, we're going to see, the Bolzano-Weierstrass direction. So if you have a metric space that is both closed and bounded, it is not necessarily compact, we're going to see. But at the very least, you have some relationship. Any questions or comments? Like I said, I'm aware that it's a lot of terminology. And I'm going to keep reminding you the definitions throughout this class. This is not the main sort of subject of this class. Ultimately, this is sort of topology. And even though it is useful, of course, and it allows you to sort of compress a lot of information, it's not the main topic of this class. So I just went over this so that you have some familiarity, and we're going to sort of use these ideas. Oh, here's a nice exercise. In an arbitrary metric space, we defined sets like closed balls, open balls, and spheres, while closed balls and spheres turn out to be closed, and open balls turn out to be open. Is closed, and any open ball is open. Okay, there's a bunch of other things. Oh, maybe I should leave that to you too. If I have a function between two metric spaces, arbitrary function, f being continuous is equivalent to saying that the pre-image of any open set in Y is open here, and likewise for closed sets. B and Y, pre-image is open, and for any closed, F in Y, pre-image of F under F is closed. So for instance, this is also another reason why it's a good idea to think about open and closed sets. Even if x and y were real lines, you wouldn't be able to say that under a continuous function, the pre-image of an open set is open necessarily. Sorry, a pre-image of an open interval is an open interval itself. But you can still say open. If you were to drop the word interval, everything works a lot better, it turns out. OK, that's a good place to stop. Thank you. I'll see you tomorrow. OK, let's start. Good morning. So small change in plans in the schedule. So originally, I was planning to just spend only 2 weeks on metric spaces. But we still have a couple more things to discuss. So originally, this week was the week when we started differential calculus, but I'm going to sort of start differential calculus next week. And so on the syllabus, you're going to see this week titled Metric Spaces 3. And so what we're going to do is we're going to have 3 weeks of differential calculus. If needed, I'm going to let go of optimization stuff. Maybe we'll come to that later. So are there any questions before we continue? So today, I'd like to introduce some more ideas from topology, and then switch over to actually proving theorems. I've been just defining a bunch of things, but I think it's time for us to actually start proving things. And this is actually related to something one of your colleagues asked about after last class, namely somehow closed sets. So closure under limits seems like, so for instance, we had this first quadrant example was about the boundary being included. Somehow, if you take a sequence in the first quadrant, you cannot converge to this point, but certainly you can converge to any point here. And it seems like this set, namely that part of the coordinate axes, consisting of y equals y positive x0 or x positive y0 or non-negative y0, seems to be sort of like where things sort of go south, right? And indeed, that is the case, and there's a certain terminology associated to this. And so here's the definition. If I take a metric space X, as usual, and if I take a subset A, then you get to define 3 new subsets, possibly new subsets, associated to A. So these are set operations that give you back sets, interior, closure, and boundary. Okay? Interior, in the textbook, it is denoted by A with a circle as a superscript. Closure is denoted by A bar, and boundary is denoted by partial A. Now, I don't like this notation, these notations, because it's not uniform. Some people use it for different things, and these notations could mean a lot of different things. And even in this class, this is going to mean something very different or slightly different later. So instead of using these notations, I'm going to say int of A, clos of A, boundary of A. I'm going to explicitly write them. OK. And so how do you define these? Well, interior is about openness somehow. Closure is about closeness. And boundary is something about what happens in between. And we said yesterday that a set is open if it is closed under small perturbations. That is to say, a set is open. Let's say you don't include the boundary. Something like this. Well, if you were to take any point here, if you wiggle it just a little bit so that you get sort of like a cloud, small ball, that's still completely inside A. So the interior of an arbitrary subset is all those points that you can perturb while still staying in A. That is to say, int of A is the set of all those A's such that for some epsilon, the open ball centered at A of radius epsilon is completely within A. Epsilon could be very small. So for instance, if somewhere in between, so somewhere in the middle, epsilon is very large, as you see. But if your point were close to this side, epsilon is going to be probably small. Okay, so epsilon depends on A. I'm not saying there is one epsilon such that it's going to work for all A in the interior, whatever. A is going to depend on A. So epsilon is going to depend on A. Closure is going to be, again, sort of like a reverse engineering of the idea of the closed set. So you're going to say, oh, so this is not going to be necessarily a subset of A, but it's going to contain A possibly. It's going to be a strictly larger subset possibly. Namely, it's the set of all those points that you get to approximate using sequences in A. So this closure of A is x infinity in X, such that there is some sequence A bullet in A that converges to x infinity. Okay. Okay, or in fact, what I can write is to be somewhat more uniform. Another way to say this is x infinity such that for any epsilon, A contains some point in the epsilon ball centered at x infinity. So let me delete this. Infinity. For any epsilon, the open ball centered at x of radius epsilon intersects A. So epsilon is your error margin, and this is saying that x is in the closure of A insofar as for any error margin you can approximate, you can find a point in A that is epsilon close to this point that you're trying to approximate. Okay? And boundary is sort of like both of them and neither of them simultaneously in a sense. That is to say, boundary of A is the points that you can approximate within A and without A also. So this is the set of all those x's such that for any epsilon the epsilon ball centered at x contains some point in A, but also contains some point that is outside A. So take away A. So this is the set of all those points that are in this ball, but not in A. This too is, I want non-empty. Okay, so here are some examples. Again, my suggestion is to first focus on the case of the intervals, calibrate your intuition, and then sort of generalize. So for instance, if I were to take an open interval, take its closure, closure of lambda rho, endpoints not included, is what? Right, so you can certainly, you're going to have every point that is already included here, because there are constant sequences. So everything inside the set is already included in the closure, but also you can approximate lambda using points in lambda rho, and likewise rho. On the other hand, if I were to take the interior of this, it would give me the open interval. Right, because any point in between, strictly between lambda and rho, well, there is some epsilon such that I can wiggle that point around without escaping the set. But if I were to take lambda itself, if I were to take lambda and wiggle it around, remember I told you yesterday, this perturbation, when you're doing this perturbation, you don't get to choose the direction. So you have to allow both moving to the left and to the right. And if you were to take this point lambda, this is your lambda, this is your rho, and this is your set. If you were to take this lambda and wiggle it around, possibly you're leaving the set. Okay, you're perturbing lambda a little bit, and sometimes you're leaving. And so lambda cannot be in the interior. That's how you argue about this. Okay. And of course, if one side was open and one side were closed, again, I would get the same thing. So for instance, this is also the closure of lambda rho, one side included, the other side not. And likewise, this is the interior of let's say this guy. And what is the boundary, of course? Let's say either one of these sets. Well, it's going to be the set containing of 2 points, that contains 2 points, which are the endpoints, lambda and rho. Right, so when I'm looking at the boundary of a set, I'm looking at all those points that I get to approximate using points inside the set, as well as point outside the set. This is the set that contains only 2 points. Okay. Right, because again, let me draw this picture. This is the lambda, this is the rho. I'm looking at now this open interval, and I'm saying that, so, question?
Oh, I was just wondering why rho is
This means I'm not including the endpoints.
Or right next to it.
Oh, this is just, you can just take the interior of any set whatsoever.
Okay.
So this is a set. I'm saying the interior of this set is, again, this set.
Okay. Oh, I see.
Okay.
Thank you.
So let's think about this. I'm saying that the only points that you get to approximate from within and from without for this set are this point and this point. Why is that? Well, certainly, lambda I can approximate from within. So this is my target. Here's a sequence that approximates lambda from within. Okay. But likewise, I can approximate it from without by choosing a sequence like this. Now, the point here is that if I were to take, for instance, the midpoint, this is not in the boundary. This I can still approximate from within, of course. But from without, I cannot approximate. Any sequence that's going to converge to the midpoint eventually is going to start hitting the open set, open interval itself, right? So that means that you cannot approximate from without. Therefore, it's not in the boundary. Now, with intervals or subsets of the Euclidean plane, whatever, these are easier to sort of visualize. But you can imagine these apply in abstract metric spaces, in particular in function spaces. So there, it becomes slightly harder to visualize what is really happening. I should also mention that, for instance, the interior of the open interval itself is itself. And the closure of the closed interval is, again, itself. And in fact, what you can say is that a subset is closed if and only if it's equal to its closure, and a subset is open if and only if it is equal to its interior. So I'm gonna leave that as an exercise. Interior of A equals A. A is closed if and only if its closure is equal to itself. And in fact, what you can say is that the closure of any subset whatsoever is the union of the interior and the boundary. Okay? And how we should think of this is like this, right? So let's say you have an algorithm or whatever. There are sort of like the typical cases. These work under small perturbations, small errors, whatever. And there are edge cases. That's how we should imagine. OK. In fact, here's another exercise that is very nice. The interior of any subset whatsoever is the largest open set contained in A. And likewise, the closure of a subset is the smallest closed subset that contains A. So these are somewhat dual notions. So closed subset that contains A. In other words, you imagine the collection of all closed subsets that contain A. Then you take the intersection of all of them. I gave as an exercise yesterday, well, I gave the dual exercise, but it's still true. Arbitrary intersection of closed sets turn out to be closed. And so when you take this intersection, that itself becomes a closed subset, and that is the closure. And then int of A is the largest open subset contained in A. So somehow these operations of interior closure or open set, closed set, these things, they turn out to be very compatible with the standard set operations that you learned in 3210, for instance, intersections, unions, and stuff like that. And of course, you also learned probably that intersections correspond to the logical operation of and union corresponds to the logical operation of or. So somehow, this is, in a sense, it's very close to logic. Yes?
Is there like a third term, like A is crazy if it's equal to its boundary, or I suppose Y or E might be another term?
Yes, probably that I would want to say something like nowhere dense. Yeah, so somehow there's like higher order sort of versions of these, which you're going to learn if you take the topology class after this. And in fact, it is related to one of the three main theorems in metric space theory. But I don't think we're going to cover it. So I don't want to go into it. OK? So yes. Yes. So somehow, imagine what type of a set is equal to its boundary. So for instance, in the plane, right, and R2, imagine the unit ball, let's say closed ball, centered at the origin. That's a closed set. Its boundary is the unit sphere. The boundary of the unit sphere itself is itself. So somehow, the boundary of a set being equal to itself somehow relates to the set having no thickness. So like a ball is like it's like almost like a two-dimensional object, if you want. A sphere is a lot, a circle is a lot thinner compared to a ball or a disk. So yes, that's a good point. Yeah. Any other questions? OK. So maximum principle. This is more important as far as I'm concerned, at least for this class. I'm going to write it there. Maximum principle or extreme value theorem. So let me write it like this. I'm going to write a theorem, and it's going to have three conclusions, and one of those conclusions is going to be the maximum principle. The other two are somewhat related also. Let X be a metric space, A be a subset. Okay? If A is compact, that is to say, let's remind ourselves, a subset is compact if any sequence in it has a convergent subsequence. So closed and bounded interval. That's how I'm imagining it. Then any continuous function defined on it is bounded, taking values in any metric space. For any metric space Y, the collection of continuous functions from A to Y is included in the collection of bounded functions from A to Y. So any continuous function defined on A, taking values in Y, is a bounded function. Okay. Second one is the maximum principle. Maybe in fact, we'll do something else. We'll leave the maximum principle as a third item. Let's say that for any metric space Y and for any continuous function defined on A, taking values in Y, the image of A under the function is itself compact. That is to say, continuous images of compact subsets are compact. For any metric space Y and for any continuous function f from A to Y, f of A, so this is the image set. This is a set consisting of all those f of a's, lowercase a, such that lowercase a varies in uppercase A, is compact. And finally, for any continuous and bounded, I don't need to say this, but you're going to see why I'm saying it in a second. For any continuous and bounded function defined on A taking real values, f attains its max and min. Okay. Now, before I start the proof of this, just want to give an exercise. And this exercise might show up in the problem set 4. Namely that, in fact, it turns out that each of these statements is, in fact, equivalent to A being compact too. So this is an if and only if statement. In other words, A being compact is equivalent to this, equivalent to this, and equivalent to this. It's a very nice exercise, actually. Exercise. Maybe in P set 4. So 1 is equivalent to 2, which is equivalent to 3, which itself is equivalent to A being compact, in fact. And that is why here I needed to say continuous and bounded explicitly. OK. But the more useful part certainly is assuming A is compact and going forward. And yeah, so let me also reiterate. This is the maximum principle or the extreme value theorem. Any real valued function, continuous and bounded, on my compact subset attains its max and min. This is the maximum principle. Okay. Let's see. Let's start with the proof of 1. So we're assuming that A is compact. Any sequence has a convergent subsequence in A. Right? That's the definition. That's the definition that I gave yesterday. In the textbook, though, you're going to see a different definition. Uses something called an open cover. I think that is harder to digest. It's useful and more applicable more generally. But I would highly recommend that you get used to this idea of taking a convergent subsequence. So the Bolzano-Weierstrass that you know already sort of makes it sound more familiar. I think that is very useful. So fix a metric space Y and a continuous function So how can we argue that it is bounded? Well, what you can do is you can say it's not bounded and try to come up with something. Right? Suppose f is not bounded. I'm going to take it slow in the proof here, try to give more definitions and more details, because I realize there's a bunch of like new terminology here. Just want you to get a little bit more comfortable. Suppose f is not bounded. So which type of a proof I'm going for? There's a bunch of names. What is this called? What is the proof tactic, if you want? Contradiction, right? So I'm going to try to come up with something that is absurd. The Latin name, I think, is reductio ad absurdum or something. OK. What does it mean for a function to be not bounded? You look at the definition. It says that a function is not bounded if its image is not bounded. That is to say, this image set is not a bounded subset. The image set f of a is not a bounded subset of y. OK. What does it mean for a subset to be not bounded? That means that its diameter is infinity. OK, what is the diameter of a subset? It's the sup of all the distances between any 2 points. So recall, let's write it like this. Diam of f of a is the sup of, let's say, y1 and y2, distance between y1 and y2, where y1 and y2 come from f of a. Right, here's a picture. So this is my bigger set, bigger space. And in it, I have the smaller set. How do I come up with the diameter? I just look at the pairwise distances. Take these 2 points. OK. Seems like this is sort of the diameter. Of course, in the standard case, in the Euclidean case, if you were to take a ball, the diameter in this sense would be literally the diameter of the ball. But this applies in any metric space. Okay. Now, so this is, as you see, as y1 and y2 varies in f of a. This is a number. So this is a set of real numbers. And I know what it means to take the sup of a set of real numbers. I'm saying that the sup is infinity. When can that happen? Right? So that's what it means for this thing to be unbounded. Right? And in fact, what I can say is, what does it mean for a point to be in f of a? That means that instead of looking at this, I can look at f of a1, comma a2. Right? Because y1 being in f of a, by definition means y1 is of this form for some a, and likewise for y2. I'm just opening up the definitions. Any questions so far? OK. So I'm saying that the sup of this, so this sup is infinity. So it's not bounded from above, this set, which means that for any n, I can find 2 points, a1n and a2n, such that the distance between their images is bounded from below by n. So there are 2 sequences then in A, such that for any n, the distance between the image of the first sequence at time n and the image of the second sequence at time n is bounded from below by n. Okay? Now, we assumed that A is compact. A1 bullet is a sequence in A. I don't know if it converges, but I know that it has a convergent subsequence by definition. A is compact. Hence, so the problem here that we need to handle is the following. I can find a convergent subsequence of this and a convergent subsequence of this. But somehow these subsequences have to be synchronized. Okay, so I need to be sampling out the correct times that allow me to say that both this and this converges in the same time. So I'm going to have to do 2 subsequences, in fact. Hence, there is a j, strictly increasing function, such that a bar 1 bullet, defined as a1 bullet composed with j, converges to, let's say, a1 infinity bar, which is a point in A. So these are my times that I sampled out. Now, instead of, this is a trick, instead of looking at the subsequence of this guy, first I'm going to look at the subsequence associated to this, then I'm going to further subsequence, take a further subsequence. That's going to allow me to sort of synchronize the times. Okay. A 2 bullet composed with j. So the nth term here is a2 comma j of n. Okay, so this is nth term equals a2 comma j of n. This is a subsequence in A, or this is a sequence in A. And again, because of compactness, there's some other strictly increasing function, let's say k, such that if I were to look at the corresponding subsequence of this, that converges. There's a k. Let me delete this. Such that a 2 bullet bar, defined as a 2 bullet composed with j, composed with k, converges to, let's say, a2 infinity bar, point in A. But of course, the point here now is that I can further take the subsequence of this compared to using this sampling. But I know that, just like in 3210, if a sequence converges to some point, any subsequence of it also converges to the same point. In fact, maybe I should have called this a hat. And then a bar 1 bullet defined as a hat 1 bullet composed with k, which is a 1 bullet composed with j composed with k converges to a1 infinity bar. So ultimately, I was able to come up with one subsequence. So it's a set of times that goes to infinity, such that if I were to just focus on those times, both this guy and this guy converges to some point in A. Okay, I was able to construct subsequences of both of these that converge synchronously. I was able to synchronize their convergences. Okay. Now, since these are subsequences of the original sequences, I know that their image too, so the distance between their images goes to infinity. But I also know that since f is continuous, the image of this first subsequence converges to f of a bar 1 infinity and f of a bar 2 infinity converges to f of a bar 2 infinity. Sorry, this is supposed to be a bullet by continuity. And furthermore, in fact, we had shown that any metric on any metric space is continuous itself, which means that the distance between these two converges to the distance between these two. Let me say comma n if you want. Converges as n goes to infinity to the distance between these two guys. Which cannot happen because this distance is bounded from below by n, a contradiction. That was the end of 1. Okay. How many of you did I lose? Probably because of this J and K stuff.
Wait, where's the contradiction?
Distance between these two is bounded from below by n.
Oh, right.
Yeah, goes to infinity. This sequence goes to infinity. That cannot converge.
And then we're saying dy is continuous. Is that from like an exercise?
We actually showed this last week.
Oh, okay.
Remember, we had shown reverse triangular inequality.
Right.
And then based on that, we were able to prove that any function, any metric, so this I can imagine as a function going from y times y to non-negative numbers. We show that that is continuous. Yeah. So just to open this up, this is like a sort of compressed way of looking at subsequences and stuff like that. But let me try to describe what is actually happening here. What is this J function and stuff? We're still not done with the proof of the theorem, by the way. We just proved the first part. We need to prove the second and third parts. but still. Interlude, I guess. So when I write A1 bullet as a sequence, right, when I write this, I told you that this bullet notation is sort of shorthand to say that it's a sequence. And in fact, what is a sequence? It's a function defined on, let's say, non-negative integers, taking values in A. Okay? And what is happening with this bullet? The bullet just says that that is a placeholder. Typically, I'm used to saying if f is a function, its output is f of, you open parentheses, put the input, close parentheses. But since sequences are sort of special functions in a sense, they're like of a specialized type, if you want, I'm saying the input is going to be time n, and the output is going to be, I'm going to write as a1 comma n, instead of saying, open paren, n, close paren. Are we happy so far? Okay. Now, this j and k are supposed to be strictly increasing functions from the non-negative times to itself. Okay, and so that means that, well, j of 0, let's say, j of 0 is supposed to be a non-negative number. So this is certainly the case. And then I'm saying j of 1 is going to be some later time. J of 2 is going to be some later time, and so on. And in fact, what you can say is that j of n for any n is going to be bounded from below by n, because they're at most, so the optimal way to take a subsequence, perhaps, is to say j of 0 is 0, j of 1 is 1, j of 2 is 2, which means that at time n, at least j of n has to be n. Okay. So when I write A1 bullet composed with j, that is a subsequence of this sequence consisting of the terms, the times specified by this j function. Okay? So this means okay, this is again a sequence in A. At time n, I'm saying, where is my signal? What is the value of my signal? The value of my signal is, first I feed this to j. I have another time, j of n. Then I take that time, feed it into this function. So function composition. Okay. So in standard notation, you would write n sub k and stuff. And typically, when it comes to more sort of qualitative fields, you don't really care that much about what that subsequence is. But there are certain situations where you need to be very careful about the sampling that you're doing. And so let me also reiterate or open up why I'm calling these samples and stuff like that. The way I'm imagining it is like this, okay? A sequence for me, in my mind, is a strip of film, okay, or footage. I'll just do it here. Okay, this is where it starts, and then, so let's say this is x0, x1, x2, keeps going on and on. Let's write a couple more. Okay, so each of these, imagine, is a frame. And a subsequence is editing out certain frames. Let's say you don't like certain scenes and stuff. It's editing, but you don't get to move around scenes. Let's say you shot something here first, and then you shot some other thing. Maybe this is like another take. You don't get to take this and put it over there. All you're allowed to do in terms of editing is to just get rid of this part and collate. Okay, let's say I don't want this part. Go on, there's like this piece, get rid of all of these, and so on. So the time stays the same, so the directionality of time stays the same. Whatever you shot, you can get rid of certain things. You can decide to not put it in the final product, but you don't get to shift around the order in which you shot things. That's a subsequence. And why do you do this? And the point of course, taking the subsequence is so that it converges. And I told you that the limit of a sequence is really the summary. So you say, OK, so I have a sequence, and it might be doing some bizarre things. So what I'm going to do is I'm going to take a subsequence that converges. In other words, I'm going to look at that sequence, the original sequence. It behaves erratically, perhaps. I'm going to get rid of that noise, OK? And then I get to summarize. That's what compactness allows you to do. And this is sort of like the heuristic that I have in mind. This is also something that I mentioned in 3210. In the case of numbers, you don't really need this sort of like more impressionistic understanding of sequences and subsequences and stuff. But it turns out that in more abstract situations, this becomes more useful. OK, we're out of time. We're going to continue tomorrow. Thank you. OK, let's start. Good morning. So today we're going to keep working on this theorem that we started proving yesterday. It had 3 parts. Let me remind you the first part. We had proved this first part yesterday. It said that if you have a metric space X and a subset A, if that subset A is compact, then in fact, the first item that we proved was that any continuous function taking values in whatever metric space defined on A, in fact, has to be bounded. For any metric space Y, C0, A, Y, the collection of all continuous functions from A to Y is a subset of the collection of all bounded functions from A to Y. This we had proved. And then after I finished the proof, we sort of switched to an interlude about the subspace notation, bullet notation, and things like this. And we can keep thinking about these things, but I thought it would be better to move on. And instead of sort of talking more about heuristics and stuff like that, it's better for me to just give you an example of what could happen and why I'm sort of trying to synchronize by choosing specific subsequences in a sense. So the example I want to give is this. X, imagine, is the reals. A is the closed and bounded interval from -10 to 10. And let's say, so in the proof of this, we had 2 sequences, A1 bullet and A2 bullet. The first sequence, let's say, is a periodic sequence that takes n to n mod 2. So it alternates between 0 and 1. Okay, it says 0, 1, 0, 1, 0, 1. And the second sequence, let's say, is n sent to n mod 3. So now, this is again a periodic sequence. It's a periodic signal. It goes 0, 1, 2, 0, 1, 2, 0, 1, 2. Now, the point in choosing these double subsequences in the proof of this was that in the proof, I could compare the nth term of this and the nth term of this. And so I had to synchronize the subsequences that were supposedly convergent to some point here of this and this. That's why we did this double subsequence business. So a one bullet in terms of these, so in terms like if you want to think of it as a strip of film, just going to draw both of them. It goes on like this. This alternates between 0 and 1. And then this alternates between 0, 1, and 2. Of course, these are very simplistic sequences. These are periodic, and you can just say, oh, I just need to fast forward the time using the least common multiple of this. So every sixth term is going to repeat, of course, for both of them. But in a general pair of sequences, you don't have this. And so, therefore, you first use this fast forward. You take this j, for instance, take this subsequence. And of course, in this case, if I just do double time, I'm just going to get rid of the every other term. Right? So for instance, for this new subsequence of the first sequence, n equals 0 gives me 0. So this stays. N equals 1, I feed it to j. 1 becomes 2. 2, I feed to the sequence. So instead of going here, I'm going to use the second term. And then I'm going to use a fourth term, or so on. So I get rid of this, 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 this. And whatever remains, you see, is the subsequence a hat 1 bullet. It's a constant sequence that is constant to 0. In particular, it converges to 0, of course. Now, again, I'm reiterating. I cannot just say, OK, I'm going to look at the subsequence of the second sequence corresponding to tripling the time. Because again, I can say I'm just going to look at every third term to get the constant sequence. But the problem is that in the proof, I can only compare the corresponding entries. Okay? I cannot compare this entry and this entry. Therefore, what I do is I apply the same fast forward that I used for the first sequence in the second sequence. So I get rid of these. Okay. This is yet another sequence in A. Then I say, OK, A is compact. Therefore, this new subsequence of the second sequence itself is a convergent subsequence. And of course, what I can say is I can apply tripling the time of this subsequence. And then what it does is get rid of this. Or maybe I should use a different one. So red crosses correspond to this subsequence. And then see, I get this here. This corresponds to getting rid of all but every third term in the remainder. So I have this, get rid of this, get rid of this. Keep this, get rid of this, and so on. But again, I get to only compare corresponding entries, which means that the moment I apply this guy to come up with a sequence that converges out of the second sequence, I need to apply the same time change to the first subsequence too. So I need to get rid of this as well. And then this, okay? This can get confusing, so that, see, I'm always trying to compare the relative terms. If I'm getting rid of some of the terms from the first sequence, I need to be getting rid of the corresponding terms in the second sequence as well. Otherwise, they're not going to be synchronized. Okay? Now, when you learn more math and when you start reading literature and stuff like that, you're not going to sort of often see the subsequence business. What they're going to say is that up to a subsequence, I can assume that A1 bullet and A2 bullet converges. And in fact, that subsequence is the same. That's what you're going to see. There are other situations where you really care about the specific subsequences you choose. It depends on what type of a discipline or what type of a context you're handling these. Okay. I realize maybe it's still not super clear what is happening here. I would highly recommend you sort of take some time and think about it and so on. And maybe if you still feel you're kind of shaky, we can meet and discuss further details and stuff like that. Okay, any questions about this? Yeah. Do any of you have any experience with editing video and stuff? Kind of, yeah.
I used to make YouTube videos, but I stopped doing it years ago because I just haven't had ideas.
Yeah. So I mean, obviously.
I didn't make anything good. I mean, gaming videos.
None of us do. But yeah, I mean, I spend a lot of time. I've been spending a lot of time. So typically what you do is, for instance, the footage of this, there's a video track and an audio track. These are two different things. They are typically glued together. So when you cut one, the audio track, the video track, at the same step is cut. But you can separate them as well, if you want. So if you want to be more creative, you sort of separate, you separately, disjoint to sort of edit the audio track and the video track. Okay? But in the abstract situation, imagine that there is some video footage and there's some microphone. And so these are not, in principle, synchronized to begin with. Of course, there's like, in movie making and stuff like that, there's slates and stuff like that, and there are methods to synchronize them. But this is sort of, in a sense, the abstract version of this. You need to make sure that the audio track matches with the video track somehow. Okay. Good. So this was the first item. The second item was that for any metric space Y and for any function continuous defined on A, taking values in Y, the image of the subset A under F, this function, is a compact subset of Y. So the image subset F of capital A is a compact subset of Y. And finally, the third item was the maximum principle for any continuous function taking values in the reals so that you can talk about max and min. The function attains its max and min. So maximum principle for any f continuous defined on A taking real values, f attains its max and min. Okay, so let's prove 2. Assuming that I have a metric space Y and it contains function f like this, I want to show that this guy is compact. So, proof of 2. Suppose A is compact and f is a continuous function. I want to show that the image set f of capital A itself is compact. the subset of Y is compact. I look at the definition. It says any sequence has a convergent subsequence. So I'm going to take an arbitrary sequence in f of a and try to engineer at least one convergent subsequence of it. Let y bullet in the image, okay, so it's a sequence. By definition, that means that for each n, there is an a sub n in A such that y sub n equals f of a sub n. That is to say, there is a sequence in A such that y bullet equals f of a bullet. A, we assume this compact. Therefore, a bullet has a convergent subsequence. Compact. So there is a subsequence a bar bullet, right? That was my notation. This is my notation for a subsequence. So this guy is a subsequence of this. And an a bar infinity, a point, such that a bar bullet converges to a bar infinity. But if it's continuous, which means that the image of this sequence has to converge to the image of this. Let me continue here. If it's continuous. Hence, f of a bar bullet converges to f of a bar infinity. But of course, a bar bullet is indeed a subsequence of y bullets. Because if a bar bullet is a subsequence of this, well, if this is a subsequence of this, then their image, its image has to be a subsequence of this. And so I was able to come up with a subsequence of the original sequence I chose in the image that has that is convergent. So done.
Subsequence like that, is that less than or equal to, or is it like a?
It is a less than or equal to, but I'm using less than in a generalized sense.
Okay.
It's a subobject. Yeah. I don't know if you covered this in 3210. I did cover it, but there are things called relations. And this is what is called a partial order relation. Similar to this, for instance. This is also a partial order within the context of subsets. You don't get to compare any two pairs, any pair of subsets. You cannot necessarily say that this subset is larger than this, but sometimes you can. That's why it's called partial ordering. Yeah, so there's this, there's this. There's this. There's a bunch of them. They all basically mean the same thing. One of them is, so the left one is lesser than the right one. If you so choose, you can just write it in words, of course, in English. I have no problems with that. OK. Any other questions? Yes?
Can you explain that last line one more time?
This one?
A bar being less than y.
This is I'm saying this is a subsequence of this.
What is? is y bullet defined?
Y bullet initially was some sequence that I chose arbitrarily in f of a. Because I'm trying to show that f of a is compact, my aim is to find a subsequence of this that converges.
Okay.
I said, oh, this y bullet, by definition, has to come from some sequence in A.
Okay, cool.
But A is compact. This guy, maybe there are many A bullets that go to y bullet, by the way. I'm not saying that this is unique. But there is at least one, by definition.
Okay.
Imagine it being, for instance, the constant sequence, a constant function. Yes. All I know is that insofar as y bullet is in the image, there's at least one sequence that y bullet comes from.
Okay. And then a bar, which is a subsequence of a, that is a subsequence of
Yeah.
a bullet. Okay.
Yeah. I find a subsequence, I find a sequence that is mapped to y bullet. Then I use the compactness of A to say that this itself is a convergent subsequence. Then once I find that convergent subsequence of A bullet, I again apply F to it. But by definition, that image subsequence is going to be a subsequence of the sequence that I started with. And it is convergent because of the continuity of F. Yeah, the impressionistic idea is this, right? So you have some bizarre thing, and F is sort of like the shadow. You look at the shadow of it, or rather F of A is the shadow. And you say, okay, if I take a sequence here, any point here is really the shadow of some point here. Then I sample out a subsequence of the thing that converges. So I take this, then this, let's say. And then I realize it converges. Then I look at the shadow of this limit. The shadow of this limit should be the limit of the subsequence of the shadows that converges. So the limit of the subsequence of the shadows, yeah. Yeah, you see, I mean, I have all of these like stories in my mind, and as you study more and more abstract math, eventually you're going to have to start telling stories about what is actually happening, because it's very hard to keep track of the formalism in a sense. Okay. It's a very good exercise to think about sort of like a abstract result and try to explain it to your 5-year-old cousin or brother or 85-year-old grandmother, depending on your situation. Okay, any other questions? Okay, item 3. I'm not saying you're going to be successful, of course. You might fail, but there's failure and there's failure. Item 3. So now, in a sense, this is a much nicer case. Certainly what I can say is, if I have a continuous function taking values in the reals, well, I can choose this metric space to be the reals. So at the very least, immediately I have that f of a is compact, for instance. Continuous. By the second part, this subset of reals is compact. I had given this as an exercise, I believe yesterday. Any compact subset of the reals is in fact closed and bounded. So this is a closed and bounded subset. because f of a is bounded, let's say just from above for the max, of course it's also bounded from below, but because it is bounded, it is a sup, and because it is closed, that sup is included in the set. Sup of A exists as a real number by the closeness sup has to be included in f of A because it's a you can approximate it. And we said that max is when sup is included in the set, so that's the max. Similarly for min, of course. I'm not going to do the min part. Same idea. Questions? Question? No? Okay. Slowly, the floodgates are opening. I mean, this topology is nice, of course, but yeah. I'm not a big fan. Like I said yesterday, all this stuff is very close to logic somehow. All you need to do is to just come to terms with this means this, that means that other thing, and then this implies that, blah, blah, blah. I don't think it's a good idea to dwell too much on these things. And so here's a bunch of exercises. Not only is an arbitrary closed and bounded subset of the reals, an arbitrary compact subset of the reals is closed and bounded, but in fact, any compact subset of any metric space is closed and bounded. Okay, what else? Oh, this is a nice one. If I have two compact subsets in two metric spaces, I can take the product metric space and I can look at the product subset. Well, compactness of both is equivalent to the compactness of the product. A times B, which is a subset of X times Y, is compact. Okay. What else? Okay. Any closed ball or sphere in RD is compact. And then Bolzano-Weierstrass and what is called Heine-Borel. I'm just going to leave all of these as exercises to you. Closed ball and sphere in RD. Okay, by now, I hope you trust me that if I could say this more generally, I would, and we will, but for now, it's important that this is RD, is compact. Bolzano-Weierstrass in RD again, specifically RD. Let's write it here, actually. any bounded sequence in Rd, and when I write Rd, I really mean it is an integer, okay? I'm not going to overload. You're not allowed to take d to be infinity, okay? Has a convergent subsequence. Again, I'm reiterating, d has to be an integer. No funny business. And finally, there's something called Heine-Borel, which is basically a collection of all of these ideas. A subset in Rd, the finite, okay, is closed and bounded if and only if compact. These are nice exercises. I think at this point you're going to benefit more from them by trying to prove them yourself. You have all the tools and all the types of arguments that you're going to use. Okay. Any questions about any of this? Big warning. Okay, so now I want to give some warnings as to why Rd is important here. By the end of today's class, in fact, we're going to generalize Rd to any finite dimensional normed space. But beyond that, things get a little bit more complicated. We're not going to deal with the complications, but at the very least, I want you to be aware of the pitfalls around all of these ideas. Warning. Two warnings we're going to have. Okay. Like this. And here's another warning. First warning is that it is not true that in an arbitrary metric space, closed balls and spheres are compact. This might fail in arbitrary metric spaces. Or spheres. Closed balls or spheres may fail to be compact in arbitrary metric spaces. Second warning is that even if you were to assume that the metric space has a vector space structure, say you have a normed space, even then you cannot guarantee compactness of closed balls and spheres, it turns out. That is to say, closed balls or spheres may fail to be compact in arbitrary normed spaces. norm spaces. Okay. So compactness, the way I defined it, insofar as you have a metric space structure, applies. I don't care what type of a metric space you have, what type of a norm space you have. The problem is that we have this intuition that a closed ball should be compact. In a sense, it shouldn't have, so you shouldn't be able to run off to infinity somehow. Or in other words, you should be able to always get to a subsequence that converges. These notions are perfectly valid in arbitrary metric spaces and norm spaces. The problem is that this intuition of balls being compact or spheres being compact starts breaking down. Okay, so here are the examples. Example for this, in fact, it's an exercise. Let me let x to be the collection of all integers, but instead of the standard metric, standard Euclidean metric, I'm going to use a discrete metric. Okay. I can certainly do this. Okay, it's a valid metric. And let me remind you, the discrete metric is the simplest one in a sense. You just say the distance between any two integers is 1 if they are distinct integers, 0 otherwise. This function satisfies the axioms of a metric. It's a perfectly valid metric space. Okay. But, for instance, a compact subset of this metric space, well, a subset of this metric space is compact if and only if that subset is finite, for instance. And furthermore, if I were to look at the open ball, closed ball, let's say, centered at the integer 0 of radius epsilon, well, by definition, if epsilon is less than 1, strictly less than 1, that closed ball is going to contain only 0. Because, for instance, for epsilon equals 1/2, there is no other integer that is 1/2 close to 0, other than 0, with this metric. Any other is 1 distant. This is where things get very bizarre. On the other hand, the moment epsilon becomes 1, for instance, in fact, in the unit ball, you have every single integer, because every single non-zero integer is 1 distant exactly. This is a very, axiomatically, this is true. This is very bizarre, okay? And in particular, for instance, the closed unit ball here is not compact. It contains everything. And by this, it cannot be a compact subset. Okay? It's very bizarre. And this is one instance of sort of the mathematical method. We have, certain experiments coming from sciences and stuff, and mathematicians look into the sort of underlying structures, and then they define things very carefully, and then it turns out that the moment you define things very carefully, you can just somehow, you immediately start creating bizarre loopholes that have to be true. Okay, so this is sort of like the legalese part of math in a sense. The moment you sort of rigidify certain concepts, there are bizarre things that also apply, that also satisfy those rules. We're not going to spend too much time on things like this, because clearly this is like an edge case. The moment you see this, you say, I hope, probably you shouldn't be doing this, right? It's like, but this is the general rule. We know from the last century that if you try to break math, you're gonna be able to break it. Okay? There's a bunch of bugs around. And here's perhaps something more important. I'm saying even in the normed space case, I can break this compactness of the closed ball. And this is actually a foundational example, and I'm going to say a couple words about it in a second also. Now imagine, I'm going to define a vector space now. I'm going to define the vector space to be the collection of all real sequences that are square integrable, square summable, let's say. And so a typical element in my vector space is going to be a sequence in reals such that n from 1 to infinity x sub n squared is a finite number. Okay. And in fact, what I'm going to say is that the norm of a sequence here, that is to say the norm of a vector, is the square root of this expression. In fact, what I can say is this. In fact, it's an inner product space. Take two sequences, multiply the entries entry-wise, and then add it up. That's an inner product. This satisfies the axiom of an inner product. In particular, Cauchy-Schwarz holds. Okay. And certainly, if this is square integrable, and so is this, then I know that the absolute value of this is bounded from above by, well, the norm of this guy and the norm of this guy. But if both of these are square summable, that means that this is a finite number. This converges. So this makes perfect sense. This is an inner product space. This is actually what is called little L2 as a space. It's a foundational sort of space where you sort of do analysis. And in a sense, you see, if I just looked at sequences that became 0 after, let's say, time n, that is basically Rn. This is just Euclidean distance in infinite dimensions. This is a standard sort of generalization of, of the plane with the standard Euclidean distance to infinite dimensions. Except that the closed ball or the closed sphere here is not compact. So consider the sequence. So now, because I'm trying to come up with a sequence here, I need to come up with a sequence of sequences. x1 bullet, x2 bullet, x3 bullet, and so on. And I'm just going to look at the standard unit vectors. So this guy is 1 only at the first entry and 0 otherwise. This, the second vector, is 0 in the first entry, 1 in the second entry, and 0 again. And this is 0, 0, 1, 0, and so on. So xmn is going to be 1 if m equals n, 0 otherwise. Each of these vectors are unit away from the origin. So they're in the unit sphere in this vector space. I'm going to leave it to you to verify that these don't converge. This sequence has no convergent subsequence. Okay, you can realize that between any two terms here, the distance is, what is it, √2. Okay. Again, this is not really our concern, and I'm not going to further develop it. But I just wanted to introduce you to this idea. It's a very foundational example. Okay. In terms of signal processing, you would think of this as a space of signals with basically finite energy, L2 energy. Okay. So the problem isn't that the terminology that we learned doesn't apply here. The problem is that intuition starts breaking down. So the moment you're not in RD, or in a second we're going to see in a finite dimensional normed space, you have to be very careful. Now it turns out that because notions like compactness and so on are so useful, there's a bunch of sort of tools, theorems, and sort of results that you can use, even in these more sort of adverse situations. So for instance, even though this compact if and only if closed and bounded breaks in arbitrary metric spaces, if you were to change this boundedness with something slightly stronger, which is called total boundedness, then it works, for instance. And in the context of normed spaces too, there is again something that allows you to take a sequence of bounded functions and come up with a convergent subsequence. But we're not going to talk about these things. Okay? If you were to take a more advanced class in analysis, ultimately you're going to have to learn these also. So in this class, I think what I'm trying to do is to just introduce you to some ideas, but not develop them unless they're foundational or they're sort of central to our concerns. Yes?
What are we proving in the second exercise?
The warning. So the exercise is that this is an example for the warning. So these are all in the unit sphere centered at the origin, but this doesn't have a convergent subsequence. Therefore, the unit ball in this space is not compact, or unit sphere. So maybe I should write it. I'll write it here. Centered at 0 in E is not compact. They are still closed, you see. They are still closed, but they're not compact. Closeness implies, compactness implies closed, but not vice versa. Closed is better. If you want to have, if you're going to have something, you want to have compactness. If you don't have compactness, you still want to have closeness. Sometimes you also don't have that, but never mind. In fact, let me finish with this. Two, if you don't have closed, at least you want to have the next best thing, which is denseness. That is to say, a subset in a metric space is called dense if the closure of that subset is everything. So you get to approximate any point in your space whatsoever. Dense if closure of A equals the whole space, which is to say you get to approximate any point in the larger space to whatever error margin you choose using things in A. You get to approximate anything using points in A. An example, of course, is that by the Archimedean principle, rationals is dense in reals, for instance. Example, rationals is dense in reals. Okay. We have a couple more things to discuss, and we have one more class. And then we're going to switch over to differential calculus. Okay. I think that's a good place to stop. Thank you. I'll see you on Friday. Well, I guess it's time to start. Good morning. So today is our final official day on metric spaces. Starting from next Monday, we're actually going to start doing calculus proper. We have a couple of things to discuss. Some ideas around generalizations of things like Cauchy sequences that you learn from 3210 in 3210, or completeness for metric spaces. And I had mentioned on Wednesday, and I had promised, in fact, in class, that things like Bolzano-Weierstrass and this Heine-Borel theorem, which says that compact subsets are, you can think of them as closed and bounded subsets. I gave as an exercise that was that these things work in RD, but in fact, they work more generally in any finite dimensional norm space. So for instance, in a matrix space, these kind of things work. So we have to discuss how or why, indeed, that is the case. So we have a couple of things, and then we'll be on our way. Before I continue, are there any questions? Hopefully, by the end of today, you're going to get your results for midterm 1. There's still a couple people whose exams haven't been conducted, so I might sort of hold off on disclosing the solutions, but at the very least, I hope you'll get your grades. Problem set 4 is not ready yet. It's almost done. You're going to get it by the end of today also. Yeah, so that's that. So remember, a while ago, I had discussed all of these different types of structures that we use in this class: inner product spaces, norms, and the metric spaces. And then within metric spaces, we said that there were a bunch of different structures. So far, we were really focusing on this continuity structure. It was sort of like a substrate. And I said there's also something called uniformity. And there's, again, something called, like certain things that come from the metric space having this d function, the distance function. And so associated to these different substrates of, or levels of structures, there are certain notions. So first of all, this is stuff about metric spaces, or things that you can talk about once you have a metric. Namely, if you have two metric spaces x and y and a function f from x to y, then you call certain extended real numbers the Lipschitz constant, Lipschitz coconstant, and the Lipschitz bolicity of the function f. Namely, what you do is you look at this rise over run. Right? So you take 2 points in your input space, x1 and x2. Look at their images under f. So these two are now 2 points in y. And then you look at this rise over run. Okay? So how much the outputs vary relative to the variance of the inputs. And then you look at the soup of that. And that is called the Lipschitz constant. In principle, this could be infinity, but at the very least, it's an extended number. Lipschitz coconstant is the same thing. So instead of uppercase, I use the lowercase lip. And instead of looking at the soup of the set, you look at the inf of the same set. And bolicity is the ratio of them. Okay? Now, this should remind you of the operator norm. In the case of a linear transformation, in, I think, the previous problem set, there was this problem about, the operator norm can be considered as a soup of rise over run again. You were only looking at the image of one vector, but that was sort of, if you really think about it, it's really the same idea. And likewise, this is the operator conorm, and this is the operator bolicity. Somehow, therefore, these notions generalize operator norms and stuff to possibly nonlinear spaces and possibly nonlinear functions. But they basically serve the same purpose. I'm going to call f Lipschitz if its Lipschitz constant is a finite number. So Lipschitz is analogous to a bounded linear operator. The operator norm is finite, is what I'm saying. Okay. What else? I'm going to call f bi-Lipschitz. In fact, let me say it like this. Yeah, I mean, let's do it like that. If I'm going to call f bi-Lipschitz if the Lipschitz constant is finite and the Lipschitz coconstant is positive. Okay. What else do I want to say? I think that's enough. So here's a nice exercise. If you have two norm spaces, V and W, and a linear transformation, A, let's say from V to W, then the Lipschitz constant is exactly the operator norm. So norm spaces. A be a linear transformation from V to W. Then the Lipschitz constant is the same thing as operator norm. Lipschitz coconstant is the same thing as operator conorm. And Lipschitz bolicity is the same thing as the regular bolicity that we defined, condition number. So now, next week, when we start talking about differential calculus, I'm going to tell you something along the lines of the following. Namely, I'm going to say, insofar as we're concerned, there's in fact two different senses of differentiability. Or in other words, you can think of differentiability of a function at a point in two different senses. One sense is a strong sense, and the other sense is the weak sense. Okay? Strong sense is, we're going to say, that a function is differentiable at a point if you can approximate it using a function that you deem is simple. Of course, in the case of single variable calculus, it should be a function whose graph is a line. And then you sort of go further, and if you want to use Taylor approximations and stuff, you say, okay, so maybe not only just a line, but any polynomial. If I can approximate my function using a polynomial, that's differentiability for me. The weak sense is control over the rise over run. So when your function is going from left to right, how much can you control the elevation, or I don't know what this is called, going down. And the second sense is weaker by way of the mean value theorem. Now, in single variable, you learn that the mean value theorem is an equation, right? So it says that in single variable, if you have a function from here to there that is differentiable, you connect the endpoints using a line segment, so you have a slope. And the mean value theorem says that somewhere in between these 2 points, you really achieve that slope, right? This is about what I call the weak understanding, weak interpretation of the derivative. And in fact, what's going to turn out is that in multivariable calculus, mean value theorem, there's still a mean value theorem, but it's not an equality. It's an inequality. It's just that you control the rise over run. So you don't get this point where the derivative is exactly equal to the slope of this, but you get something, slightly weaker. We'll get there next week. But this is all I wanted to say about this for now. So this is all there is to all I want to say about metric spaces. In terms of uniformity, again, within the context of metric spaces, here are some definitions. If I have a metric space, what do I need to define? Oh yeah, I guess at first it's better to define uniform continuity. Let xy be metric spaces. And let's let f to be a function from x to y, as over there. We're going to say f is uniformly continuous if basically the analogous definition holds compared to the definition you already know. F is uniformly continuous if for any epsilon there's a delta such that for any x1 and x2 in x, if the distance between x1 and x2 is bounded by delta, then the distance between their images 2 is bounded by epsilon. Okay. So by the way, this was the end of the definition over here. These are some exercises. Okay. And I'm going to call f a bi-uniform homeomorphism. If f is a homeomorphism, it is uniformly continuous, and its inverse is also uniformly continuous. Homeo means f is a homeomorphism, f uniformly continuous, hitting a resonance spot here, and f inverse 2 is uniformly continuous. Nice example to keep in mind is x cubed, for instance. X cubed is a homeomorphism from the reals to itself. It is an inverse. It's not a diffeomorphism. That's a critical point. But it's a homeomorphism. It's continuous, has a continuous inverse. It is uniformly continuous, but its inverse is not uniformly continuous, for instance. So you need to say both f and f inverse is uniformly continuous. So the point, of course, is that when we have this notion of homeomorphism, without this uniformity business, we're in the world of continuity or topology. And homeomorphism means that two spaces are indistinguishable from the perspective of topology. Likewise, in the context of uniformity, you want to have a bi-uniform homeomorphism. That's a type of transformation that preserves a structure. OK. Cauchy sequences, completeness, and so on. If I have, so I have x here. I'm going to call a sequence in x Cauchy if the definition you're familiar with holds using the metric. Cauchy sequence if, so instead of having a limit necessarily, now what it is that after finite time, I want this sequence to have bounded volatility. So one term next to the next one, let's say, I don't want them to jiggle too much. So for any epsilon, there's an n. Let's be a little bit more explicit, perhaps. For any epsilon positive, there's an n integer. I wait finite time, such that if I were to compare any two terms after this, capital N, yeah. So I'm comparing the nth term and then n plus pth term. I want the distance between them to be bounded from above by epsilon. An important exercise, I guess there are a couple exercises that I want to mention. Let me start listing them down here. Connecting the metric world with the uniform world. Lipschitz implies uniformly continuous, which itself implies continuous. That's one. Another thing, another exercise that connects topology to uniformity. Any convergent sequence is Cauchy, and any Cauchy sequence is bounded. Okay. Now, it turns out that it is not the case in general that Cauchy sequences are convergent. This is something special about the reals. And in general, we're going to say that a metric space is complete if any Cauchy sequence is convergent. X is complete as a metric space if any Cauchy sequence is convergent. So the heuristic here is the following. If you have a signal that you know asymptotically becomes less and less volatile, you call the space in which your signal takes values in complete insofar as that signal that keeps getting less and less volatile actually stabilizes somewhere. Okay? So you're not able to sort of fall out of the space somehow. There's a limit. Okay. And so, for instance, some of your colleagues were mentioning things like this. You call, so we have phrases like Hilbert space or Banach space. Let's define those as well. Maybe I can define it here. A Hilbert space, Hilbert was a mathematician, much like Cauchy, space is nothing but an inner product space that is complete in this sense. So in any inner product space has a norm. Any norm induces a metric. So any inner product space is a metric space. And so I can ask, is this inner product space complete or not? That is to say, in this inner product space, if I were to take a Cauchy sequence, am I guaranteed that Cauchy sequence is actually convergent. If yes, then you call this a Hilbert space. So complete inner product space. Complete inner product space. Banach space means same thing, but you start with a normed space. Banach space, yet another mathematician. Complete normed space. These are definitions. And if you were to take more advanced classes in analysis, you're going to study. So these are going to be the main objects where you sort of do a lot of calculations and proofs and stuff like that. I'm just introducing these ideas to you. For us, it's not going to matter too much. Because it turns out that any finite dimensional normed space is essentially one of these. So this terminology becomes more useful once you have sort of infinite dimensional spaces. Even though we're going to be using some infinite dimensional spaces, that is not our main concern in this class. OK.
Can I ask a question?
Yes.
Wasn't there a theorem that said a sequence is Cauchy if and only if it converges?
Well, that was for reals.
That was for reals?
Yeah.
OK. But in terms of like real, I guess, real spaces, X is always complete?
Any Euclidean space is complete, yes. Okay. That's an exercise, of course. So I was going to write that, yeah. Let me see. Is it that? Yeah. Here, let's write this. So RD is complete. Right, so what is a Cauchy sequence in RD? It's the many Cauchy sequences in reals. But you know that Cauchy sequences in reals converge. So this has to converge. Another thing, if I have a compact metric space, or let's put it this way, if I take a compact subset of a metric space and take a continuous function on it, then in fact, that continuous function is uniformly continuous. You've probably done this in 3210 using a closed and bounded interval. You're going to realize literally the same proof works in this more general setting. OK. That's OK. Now, when we start talking about differential calculus in higher dimensions, again, we're going to have this strong interpretation of differentiability, namely approximation by simple objects. And so this next exercise I'm going to state is an indication that indeed linear transformations, or more specifically bounded linear transformations, is the correct choice, or one of the correct choices for the simple object with which you want to approximate things. This exercise ultimately says that pretty much all of these notions coincide for linear transformations. One part of this we had already proved, but I'm going to restate it for convenience. norm spaces. And let's let A to be a linear function, linear transformation from D to W. Then the following are equivalents. Okay, first is, of course, boundedness as a linear transformation. So A having finite operator norm. This is equivalent, we had proved in class that A is continuous at 0, which itself is equivalent to saying that A is a continuous function. Equivalence of these three we had shown already. Now I want to add Lipschitz property and uniform continuity as well. And these two are equivalent, in fact. So somehow, once you have a linear transformation, all of these different notions turn out to be pretty much the same thing. But of course, this is not the same. This is not to say that these are equivalent for arbitrary functions. Okay? For calculus, we're going to have to, so we're going to be using nonlinear functions. The point of this exercise is to convince you that, yes, it's a good idea to try to approximate nonlinear things with linear things. Simplifies the things, well, the objects that you're trying to handle. Okay, any questions about any of this? I know it's a lot, but I want to be done with metric space stuff, continuity stuff, move on. We did plenty, and I think you've been exposed to some of these ideas. I think it was sufficient. What I do want to talk about is, well, finite dimensional normed spaces. This is going to be important for us. Theorem. If I were to take, so this works in two steps. In the first theorem, I want to say something about linear transformations defined on the good old RD, taking values in an arbitrary normed space. Then I want to sort of generalize it a little bit. I take an arbitrary normed space W. Maybe it's infinite dimensional. But what I'm interested in is linear transformations defined on the concrete space RD. Then the collection of bounded linear transformations defined on RD, taking values in W, is the same thing as the space of all linear transformations. In words, this means that any linear transformation defined on RD is automatically continuous. Okay? Why is that? Because we had shown in class that continuity, oh, it's here. Continuity of a linear transformation between any two norm spaces whatsoever is the same thing as saying that the operator norm is finite. And so a bounded linear transformation is the same thing as a continuous linear transformation. Okay. Let's set A to be linear from RD to W. I want to show that this guy is continuous. Equivalently, I want to show that its operator norm is bounded. So once I want to show that its operator norm is bounded. By the way, when I write this RD, of course, if I don't say anything, you take it with the standard Euclidean norm or Euclidean inner product, whatever. And so how do you bound the norm, the operator norm of a transformation? Well, you just take a vector. There are multiple ways to do this, of course. But let me just use a definition that I used in class. So all I need to do is I need to take a vector v in RD and somehow control the norm of AV. Okay, in fact, let me write it like so. Any vector in RD in this concrete metric space, concrete vector space, is a tuple of numbers. I know that. That is the definition of RD, tuple of real numbers. So I can write this V as a linear combination using the standard basis vectors. So let's say beta 1, beta 2 is 0, 1, 0, dot, 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 0, and so on, all the way up to beta D, which is 0, 0, 0, dot, 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 0, 1. And these are the standard basis vectors. And certainly V can be written like so. Okay. So now I'm going to apply A to this. To be clear, I need to look at the norm of this in this output space, which is W. Okay. I just substituted, instead of E, this linear combination. A is linear, so I can distribute. Okay, so VI's here are numbers, beta i's are vectors. Okay, so I can distribute A inside. But I know that by one of the axioms of a norm, norms they satisfy the triangular inequality. So they're subadditive. If I were to take this norm inside, that norm would possibly increase. Okay. We continue from there. So that expression is upper bounded by VI in absolute value, right? VI's were numbers. By the homogeneity property of the norm, I can distribute and take the constants out as well. A beta I NW. Okay. Now, what I can do is, I goes from 1 to D. So instead of each of these numbers, for any I can just take the max of these. So this will be upper bounded by this number times the max of these expressions. It's a finite number, because I have only finitely many indices. And here's the nice thing about this specific RD. Namely, I know that the absolute value of any one of these entries are upper bounded by the norm of V itself. So this is upper bounded by the norm of the vector V. And so this is upper bounded by D times norm of V times this guy. This is a finite number. And so you see, I was able to bound the magnitude of the output using the magnitude of the input up to some constant. That's what it means for A to be a bounded operator. You're not happy about something. Maybe this?
Wait, where did the D come from?
Because for each I, I'm saying the absolute value of V sub I is upper bounded by this.
Okay.
So I'm adding norm of V D times.
Okay.
Yeah. It's a constant sum. Any questions about this? These types of arguments is sort of the bread and butter of multivariable calculus. So, yes.
This star equation.
Yes.
How did you? Why is Vi not in the argument of A? Like when you move.
So here, beta I is a vector, Vi is a number. Okay. A is a linear transformation. So first I can put it inside the summation, then I can put it inside between the scalar multiplication. Okay. Yeah.
So isn't this just the definition of the alt norm if you're looking at the maximum of A, B, AI?
Well, no, it's not the definition. Like this argument, okay, let me put it this way. Operator norm of a transformation should be independent of the basis.
Right.
Now, this number depends on the basis.
Okay, we're not going over all.
Yeah.
Okay.
Now, it's an interesting question. If you were to take this number and look at the infimum of all such numbers over all bases beta, that's still an upper bound, but I'm still not quite sure if it's the operator norm. So that might be an interesting exercise, actually. So the point here is that this number, you look at this number and you say, what does this depend on? It depends on D, the dimension. It depends on the transformation. And it depends on the basis you chose. So if you were to choose a different basis, quite possibly this number is going to be better. Maybe you're going to have a better control, right? So maybe if you can find a better basis that is subordinated to the transformation you're trying to bound, you're going to get a better bound there, in principle. Now, if you can get the best bound that way, that would be great, but I'm not quite sure if you can. Maybe you can, I don't know. That's a nice problem, actually. I need to think about that. Any other questions about this? Okay. Now, let's go one step further. Namely, we can say the following. If you have a linear transformation from Rd to W, then in fact, that linear transformation is a linear isomorphism if and only if it's a homeomorphism. Theorem. D be an integer and A be a linear transformation from Rd to W. Then A is a linear isomorphism. It has a linear inverse. In particular, W2 is d-dimensional, of course, by the classification theorem. A has a linear inverse if and only if its inverse is continuous also. In fact, what we can say is the following. A is a linear isomorphism. A is a homeomorphism. A is a uniform or bi-uniform homeomorphism. And equivalently, A is a bi-Lipschitz homeomorphism. What does this mean? This means that the moment you have a finite dimensional normed space, okay, that's what it means for there to be a linear isomorphism from Rd to W, then you have the preservation of the topological structure. Okay? Anything that works in Rd works in this finite dimensional norm space. You have preservation of the uniform structure. Cauchy sequences, completeness, everything is inherited by this finite dimensional norm space. And in fact, boundedness, things like this too, is inherited. Quite possibly the numbers are going to be different. Yes?
So W is finite?
Yeah, because of this. So I'm assuming, so in order to prove any one of these, I'm going to have to assume that A is a linear isomorphism. But insofar as there's a linear isomorphism from here to there, W has to be d-dimensional. Because the dimension is the unique invariant that classifies whether or not you have a linear isomorphism between any two spaces.
So why do we say Rd? Can't we just say any finite dimensional space?
Say again?
So can we generalize it more to say any finite dimensional space instead of Rd?
Well, ultimately, yes.
Okay.
Yes. Sure, you can do it. Because, yeah, I mean, you can take any two finite dimensional norm spaces, V and W. Let's say V is d-dimensional, W2 is d-dimensional. That is to say, there's a linear isomorphism from here to there, and another one from here to there. But of course, you can compose and sort of get an isomorphism that way too. Yeah. Okay. Now this has lots of ramifications that are very convenient. But the gist of all this business is that even though we have all of these different spaces, the moment you have a finite dimensional normed space, you can just pretend that it is Rd. Linear transformations are matrices. For the purposes of calculus, most things, 95% of things are going to work just the same. Okay? So that's the gist of it before going into the proof. finite dimensional. It has to be finite dimensional. You don't get to use this in function spaces. But for matrices, other things you can. Okay? Any finite dimensional norm space is pretty much RD. Is pretty much RD with the standard norm, standard inner product, whatever. Okay. How much time do we have? Okay, 3 minutes. So this is not a hard proof, in fact, and it's a fundamental application of the maximum principle that we discussed on Wednesday. And in fact, all I'm going to do is I'm going to show, which one? Let's show that this one. The other ones I'll leave to you. They, in fact, follow from the previous exercise I gave. So these are exercises. So for the proof, it suffices say say A has an inverse. A inverse is a linear transformation from W to RD. I know that this guy is linear. Because it is linear, saying that this guy is continuous is equivalent to saying that its operator norm is bounded. But in fact, the operator norm of A inverse is nothing but the reciprocal of the operator conorm of A. So saying that this guy is finite is the same thing as saying that the operator norm of A is a positive number. I'm running out of time, so I won't be able to finish this proof. But the idea is going to be the following. The operator norm of A, so the operator norm of a transformation was the maximal expansion, whereas the operator conorm was the maximal shrinkage. What I'm going to try to do to prove this is to verify that A, in fact, doesn't shrink too much. Okay? That's what I'm going to try to do. We're going to continue talking about this on Monday, and then switch over to differential calculus. Thank you. Have a nice weekend. I'll see you on Monday.